Hello and welcome back to Calero Academy. If you watched our last video, we promised you a part 2 where we would investigate the corollaries. So here they are. First of all, if you remember, we proved in the last video that the probability of n on 2 heads in n tosses of a coin is equal to the probability of n on 2 heads in n minus 1 tosses. So, what we're going to try to investigate now is, does this actually hold for all positive n and m? Does it? So, let's take the most extreme example. Let's try n is equal to 2, for example. Note, n can't be 0, n has to be more than 0, because although 0 could be technically an even number, 0 would make the factorials, would make n minus 1 negative, which doesn't exist in probability. So, does it work for n is equal to 2? So is the probability that one head in 2 tosses is it equal to the probability of one head in 1 toss? Now, this seems too good to be true. Surely there's something weird going on there. But now, instead of just resorting to binomial PDFs, let's draw our event box. Let's draw the sample space of all things that could occur in 2 tosses. So we have a tail and a head and a head, a head and a tail, and a tail and a tail. And it turns out that the head occurs exactly once in 2 out of 4 times, so it's equal to 1/2. And of course, one head in 1 toss is also equal to 1/2. So it does actually hold for all positive n, for all positive even n. So that's a very interesting fact. Now, would this thing work for, say, n minus 2 tosses? Would the probability of n divided by 2 heads in n tosses be equal to the probability of n on 2 heads in n minus 2 tosses? And say n minus 3 tosses? Would it be generically true for all n minus a, where a is some constant? As it turns out, it's not actually generically true. All we have to prove to show that it's not generically true is to find one example where it's not true. And so let's just make the math simple and pick n minus 2. What we're going to do now is prove that the probability of n on 2 heads in n tosses is never equal to the probability of n on 2 heads in n minus 2 tosses. N being greater than or equal to being greater than 2, and also n being an even number, 0 mod 2. So, we're going to expand these guys a little bit, and then we're going to do a proof by contradiction. So, let's first expand this guy. It's a binomial function, so we can write it as the probability is f of n, x, and p is equal to the n choose x times the probability to the power of x times 1 minus p to the power of n minus x. In our case over here on the left hand side, n is equal to n, x is equal to n on 2, and p is equal to 1/2. So it's our f of n on 2, and 1/2. this is going to be equal to n, choose n on 2, times 1/2 to the power of n. Our right-hand side will be f of n minus 2, n on 2, and 1/2, which will equal to n minus 2, choose n on 2, times 1/2, sorry about that messiness, 1/2 to the power of n minus 2. So, let's do a proof by contradiction. Proof by shorthand for contradiction. So, if these were really true, then it would be equivalent to show, if these were actually equal to each other, then this would be equal to that. So, therefore, it should be that n, choose n on 2, times 1 on 2 to the power of n, is equal to n minus 2, choose n on 2, times 1/2 to the power of n minus 2. So we're going to drive down and show that it's not actually true, and that generically is going to lead us to an answer that never makes sense. So, therefore, expanding, it should be equivalent to show, let's try to be as neat as possible, it's equivalent to show that n factorial on n on 2 factorial on n minus n on 2 factorial, which is n on 2 factorial, times 1 on 2 to the power of n is equal to, expanding this sucker, n minus 2 factorial on n on 2 factorial times, let's just show the arithmetic here, n minus 2 minus n on 2 factorial, which will equal to n on 2 minus 2 factorial. N on 2 minus 2 factorial. A little messy in there. Times 1 on 2 to the power of n minus 2. Okay. Now let's do some let's get rid of the n on 2 factorials. And now let's do some multiplication to both sides. Therefore, it should be equivalent to show that when we multiply both sides by n on 2 minus 2 factorial, it should be equivalent to show that n factorial on n on 2 times n on 2 minus 1 times 1 on 2 to the power of n is equal to n minus 2 factorial divided by 2 to the power of n minus 2. All we just did there was multiply both sides by n on 2 minus 2 factorial. That will leave on this side. This will get rid of everything behind, if you want to think of it that way. The n divided by 2 and n divided by 2 minus 1 factorial. So, let's continue our destruction of let's continue the destruction in our proof by contradiction. Let's divide both sides by n minus 2 factorial. That will similarly get rid of everything behind n times n minus 1 over here. So it'll leave us on the left-hand side n times n minus 1 divided by n on 2 times n on 2 minus 1 times 1 on 2 to the power of n. And we wanted to show that it's equivalent to show that it's equal to 1 on 2 to the power of n minus 2. Now, what we're going to do now, let's get rid of all the denominator here. Therefore, it should be equivalent to show that multiplying both sides by n on 2 times n on 2 minus 1 should be equivalent to show that n times n minus 1 times 1 on 2 to the power of n is equal to n on 2 times n on 2 minus 1 on 2 to the power of n minus 2. Next, let's multiply both sides by 2 to the power of n. So if it's really equal to each other, it should be equivalent to show that it should be true that n times n minus 1 is equal to 2 to the power of n on 2 to the power of n minus 2 times n on 2 times n on 2 minus 1. Now, this over here is just simply equal to 4, because what we have left is 2 to the power of 2, and that's equal to 4, so we can rewrite that as 4 times n on 2 times n on 2 minus 1. Or, inserting that into here, that's equal to 2 outside of n times n minus 2. All we did is split the 4 into 2 times 2 and then insert one of the 2's inside there. So, if those are really true, it should be equivalent to show that n squared, expanding this guy, n squared minus n is equal to 2n, 2 times n squared minus 2n, or it's equal to 2n squared minus 4n. Let's do a cross check to make sure nothing got left behind. It's n squared minus 2n times 2. So that seems really weird, because after all, how can 4n be equal to n? First of all, let's divide both sides by n. Therefore, it should be equivalent to show that n minus 1 is equal to 2n minus 4. Or, going further, it should be equivalent to show that n is equal to 3. But that's impossible because n is even. Look, what happened here, we added to both sides 4, that gets us 3 on this side, and subtracted n to both sides. So this is impossible, and therefore, it's a contradiction. And therefore, we've proven that it's not generically true that, going back to the top, it is not actually true that the probability of getting n on 2 heads and n tosses is equal to the probability of getting n on 2 heads and n minus 2 tosses. This means that also it is not actually always true that the probability of getting n on 2 heads and n tosses is equal to n on 2 heads in n minus a, where a is some constant tosses. So, that makes our discovery of this thing being true ever the more special, because it's so neat and it's so tidy. And that was a very interesting corollary. So, this has been a Calero Academy production, and thank you for watching. If you have any questions for the work, or if you have any corrections, please enter them into the comment section and we'll look into it. In addition, Calero Academy will start taking suggestions for videos in the comment section. So if you have anything you want to show us, just put it into the comment section and we'll see if we can do it. Thank you for watching, and this has been a Calero Academy production.